Hello viewers, it's my pleasure to welcome you to another edition of Pause and Ponder, in which we are going to focus our attention on electrical conduction through solutions. A solution is a homogeneous mixture. It contains two parts, a solute and a solvent. When the solvent is water, the solutions are called aqueous solutions. When the solvent is anything other than water, we call it non-aqueous solutions. Making use of everyday household chemicals and materials available, we will try to demonstrate this electrical conduction. For that, I have over here a very simple arrangement, a bulb in a holder. This in turn is attached to a glass tube. Actually, what we have is here two bare wires in a glass tube, and this in turn is connected to the mains. The only important consideration is that the two electrodes should not touch one another. This in turn is connected to the mains. Now, to do the experiment, I have over here kerosene, sugar solution, ordinary water, dilute hydrochloric acid, glacial acetic acid in this beaker. Glacial acetic acid is pure acetic acid, which when diluted with water to a concentration of 1% is called vinegar, which we use at home for cooking. Now our first experiment is the electrode, as you have seen here, is placed in kerosene. I switch on the mains. Observe that there is no glow of the bulb. Switch off the mains. Give a wash of the electrodes. Transfer the electrode into the sugar solution and switch on the mains again. Once again, the bulb does not glow. Off. Wash and into plain water. Switch on and again the bulb does not glow. Now, while the current is, the mains are still on, I will add a little common salt known as sodium chloride. The bulb begins to glow. Let me add some more, and the bulb glows more brightly. Okay, we switch it off. We wash it once again. Now I'll transfer this into dilute hydrochloric acid solution. Let's see what happens. Oh, the bulb glows very, very brightly. Now, the final experiment of ours is placing the electrode in acetic acid. The electrode is in the acetic acid. Switch on. There is no glow in the bulb, but let me dilute it. As I dilute it, the bulb begins to glow. Let me dilute it some more. And there is a brightness in the glow of the bulb. So what is the explanation? To explain the phenomenon that we have seen, we have to turn to Svante Arrhenius' theory of ionic dissociation. Arrhenius said that when certain molecules or certain chemicals are added to water, they break into ions. The more ions produced, the better will be the electrical conductance of that solution. So we saw that in the case of dilute hydrochloric acid and water containing salt, the bulb glowed very brightly. Whereas in water, kerosene and sugar solution, there was no glow at all. It means that in water, in sugar solution and in kerosene, the molecules of sugar, water did not get ionized. Whereas in the case of acetic acid, initially there was no glow, but as we diluted it, there was a glow. This is because as we diluted, more ionization took place and there was ionic mobility. So this is the theory, and based on this, Arrhenius classified solutions which are good conductors as strong electrolytes, solutions which do not conduct electricity as non-electrolytes, and those which conduct it poorly as weak electrolytes. Incidentally, this theory was not accepted at that time by the scientific establishment. But how important it was came into being when in 1903, Svante Augustus Arrhenius, a Swedish physicist and chemist, was given the Nobel Prize. This particular demonstration has practical applications. Electroplating is one such application of this. So next time when you see an electroplated object, pause and ponder.